Hey, good evening, everyone. As I promised, the remaining portion of the class that we did not cover on Wednesday when I had to leave early due to a medical reason, I'm gonna go over with the video recording, and then of course the file will be printed out and posted on Brightspace for all of you to follow through. Now, we are going to get an opportunity to review the lecture notes tomorrow because that's going to be part of the study guide for right after the exam, the study guide for quiz pass. But it is important to watch this first so we don't have to spend a lot of time tomorrow going over this material, but we have to focus on the remaining part of it. We have to focus on um, just very briefly reviewing it and going directly to the study guide for quiz 5. So let me go ahead and then share the lecture notes. I started off these lecture notes by giving you the solution. Now, you are aware that every one of us, including myself, get a different set of the questions due to the algorithm and the design of the homework assignments in WebAssign. But I thought that number 7 in HW8 is challenging. And then I decided to go over the one that I ended up getting in my set of questions for HW8. This is about finding the extrema and points of inflections, but for an equation that I think will be challenging in terms of differentiating. So the function is given as x squared over x squared plus 75. As you are all know, and that's something that you will need for the test tomorrow, in order to find the extrema, you have to find the critical values, and then uh, critical values are computed by finding the first order derivative and setting it equals to 0. And then to find the inflection points, we have to find the second order derivative and set it equals to 0. This is how we find the possible inflection points. And then, of course, you have to go through the chart, which I believe every one of you can do it. But I'm going to go over only the part of finding the derivatives because that's what I think it will be important for all of you to see it as an additional example, as you still have time tonight preparing for the upcoming exam. And then setting them equals to 0, solving the equations, and then you can work on the table on your own. If I differentiate this function, which is a rational function, I have to use the quotient rule. So you have u over v prime equals u prime v minus uv prime all over v squared, where my function u is x squared. So therefore, u prime is going to be the derivative of x squared, and that's 2x. And then the function v is x squared plus 75. So the derivative is going to be the derivative of x squared plus the derivative of 75, which is 2x plus 0, that's 2x. If we substitute them into the formula of the quotient rule for the first order derivative, then we have u prime, which is 2x, times v, x squared plus 75, minus function u, which is x squared, times v prime, which is 2x. And then if we distribute to x on the first one, we have over v squared, which is x squared plus 75 to the second. Distribute 2x over x squared plus 75, we get 2x times x squared, 2x to the third, plus 2x times 75, 150x, and then minus x squared times 2x is minus 2x to the third. And 2x to the third and minus 2x to the third, that cancel each other out. So we have 150x over x squared plus 75 to the second. So to find the critical values, I'm going to set the first order derivative equals to 0. That's a rational equation. You solve the rational equation by eliminating the denominator. And to eliminate the denominator, you multiply both sides by x squared plus 75 to the second. And that's what I did in my next step. So denominator is eliminated on the left-hand side, and the multiplication by 0 generates the 0 on the right-hand side. So the only thing remaining on the left-hand side is 150x equals to 0. If I divide both sides by 150, the critical value is 0. And then you are going to see that this will be classified either as a minimum and a maximum. This is where you have to create the table with the open intervals, the test values, you plug into the first order derivative. I would like to remind everyone, when you plug in the test values, you don't need to consider the denominator. You don't need to plug in anything in the denominator because no matter what x is, that's positive. You only need to focus on 150x. This is where you plug in, and that's going to determine the sign. But the critical values will be used to find the extrema, either the minimum and the maximum. And then once you find them, if there is one, you're going to substitute x equals to 0 into the original function, and then that's going to give you the value of either a minimum and a maximum. So yeah, I substituted, so the extrema is going to be 0, 0. Now we're going to use the second order derivative to find the possible inflection points. And you see the word possible in there. Why? Because you still have to go through the table with the test values. It's not enough to say that the second order is equal to 0. You need to show that the graph of the function is changing from concave up to concave down or vice versa. To find the second order, you have to differentiate the first order. So that's what I'm doing in there. So I have a brand new function u and a brand new function v. It's not complicated to find the derivative of function u because that's the derivative of 150x, which is 150. But be very careful with the derivative of function v because chain rule must be applied. In this case, you have an expression of x in parentheses raised to the second. So that means you're going to use the power rule. So you're going to bring 2 in front of it, decrease 2 by 1. But you still have to multiply by the derivative of the base, which is the derivative of x squared plus 75. So this is 2 times x squared plus 75 times 2x. So altogether is 4x times x squared plus 75. And now I'm ready to substitute using the quotient rule. So u prime is 150 times x squared plus 75 squared, which is the v, minus 150 times x, that's the function u, so 150x, times 4x, which is times x squared plus 75, which is the derivative of v, all over v squared. But you already have x squared plus 75 squared, so if I square it again, that's going to be like multiplying the exponent, so that's going to be 4. I'm showing you one power rule of exponents. So when I have a squared raised to the third, that's the same as raising a squared 3 times or multiplying it by itself. So that's 8 to the 6. So we say if I raise an exponent into another exponent, we multiply exponents together. Now, rather than you distributing everything at the top, I would recommend you to factor out something that they both share, the two terms in the numerator. They share x squared plus 75, which you see highlighted in there. So I factored it out, just one. And then from the first one, 150 is remaining and still one of the x squared plus 75s. Because I had two of them. One is factored out, one still remaining. And then minus 150x times 4x. And this is all divided by x squared plus 75 raised to the fourth. So there's 4 of them. I get rid of 1, there's still 3 remaining. After eliminating x squared plus 75, what I see on the numerator, I see only 150 x squared plus 150 times 75, which is 1150. And then 150 times 4 means 60 x squared. So 150 x squared minus 60 x squared, that's minus 450 x squared. So altogether, the second order is 1150 minus 450 x squared over x squared plus 75 to the third. So all this tedious operation, that's why I decided to go over this, giving you the opportunity to see at least an example and use it for your HWA. This is question number 7. So we solved this the same way we solved the first rational equation. So we set it equals to 0, the second order, to find the possible inflection points. And then we eliminate the denominator by multiplying both sides by the given denominator. So multiplying by the denominator will eliminate the denominator on the left-hand side. So the only thing remaining is the numerator, which is 1150 minus 450x squared. But on the other side, due to the multiplication by 0, the right-hand side becomes 0. So I'm going to subtract 1150 from each side, and then divide both sides by negative 450. So I get x squared equals 75 over 3. 75 over 3 is 25. x squared is 25, which means the square root is plus and minus 5. So there are two possible inflection points, x equals -5 and x equals 5. If they're plugged into the equation, you get the outcome 1/4 for both of them. But again, you still have to create a table in order to decide if they are indeed inflection points. And that's something that you have to do on your own. And that's going to transition us into chapter 5. Now, there's one section in chapter 4 that I prefer to go over in class rather than recording a video, and that's application of optimization that still uses the first order derivative. So you're going to learn how to deal with maximization or minimization, overall optimization, by looking at two different applications. So I'm going to do maximizing a volume application and then maximizing an area application. One of them, the area application, I believe, is part of the study guide for quiz 5, but the additional example is one of the examples in our lecture notes. So I'll go over this in class. So it's not that I'm skipping section 4.7. And that's an important section because will be one of those sections that the applications of it are going to be part of the final exam. The other thing I'm going to do tomorrow, I'm going to end out the study guide for the final, which is already posted, and then the detailed solution posted in Brightspace. Now we are transitioning into the final chapter of the semester, chapter 5, even though we are only using one section of chapter 6, when you are going to see one or possibly two applications of a process that is known as integration. Remember, we started calculus by working on two major applications of calculus. One was the application of the rate of change, and then the slope of the tangent line that eventually led us to the first order derivative and differentiation as a process. Now we're going to focus on the second process of calculus known as integration. And for that will be next week a specific application of not approximating an area as we have done it at the beginning of the semester by drawing rectangles inside the given area. We're still using that idea, but expanding that idea into a precise way. And that's going to lead us to what is known as the fundamental theorem of calculus. And then a well-known process, extremely important, a process that is known as the inverse process of differentiation, and that process is integration. But I will keep it simple. I'm going to introduce the process of integration by using a very simple example. Let y be equals f of x be an unknown function. And the first order derivative of this function is given as f prime of x equals 3x squared. So that's what is given. So I don't like the breakdown of this. I'm going to change it. So let's try to back up a little bit. So what I'm saying is there's a function f of x, y equals f of x, that is an unknown function. So we don't know what the function f of x is. But what we know is the derivative of it. So we know f prime of x, and that is given as 3x squared. So in other words, the expression of f of x is a question mark. It's unknown. Now, our goal is to use the derivative of the function f of x, to use f prime of x, and find the missing function f of x. So let me start writing what we know in a different form. If I know f prime of x equals 3x squared, what is f prime of x for us? F prime of x for us is the derivative with respect to x of the function f of x, which means is the dy over dx, because f of x is indeed the variable y. So that means dy dx equals 3x squared. Now my goal is to find the y. So I'm going to replace, as I said, f prime of x by y prime, and then eventually write y prime in the form dy dx. And then change this into dy dx equals 3x squared. I'm going to consider this as an equation, and solve it for variable y. So how do I solve this for variable y? First, I eliminate the denominator, which I did it in my previous example, question number 7 of HW8. So multiply both sides by dx, eliminate the denominator. So that means dy equals 3x squared dx. And now I need to find the y. So isolate the y, isolate the f of x. Now, isolating the y is not the same as isolating when you have a normal equation. You have 2x equals 6, and then you divide both sides by 2, so you can find the variable x. This is not the same. In order for me to isolate the variable y, I have to eliminate d. And d is not just the letter d. D represents differentiation. And to eliminate differentiation, you have to use a process that is known as integration. So the inverse operation of differentiation is called integration. The operation is called integration and then is denoted by this particular sign, known as an integral sign. We read this notation as the integral of. So what I'm going to do is I will take the integral of both sides. The integral of dy, the integral sign, and the d. So the integration and differentiation cancel each other out. This is how I get the y. So the d will be eliminated, the integral sign will be eliminated, so we get y equals the integral of 3x squared dx. The form dx is used to identify what is known as the variable of integration. So if I have the integral and then I have c dx, that means I'm integrating in terms of x. If I have an integral sign and I have a dz, that means I'm integrating in terms of z. If I have a db, that means I'm integrating in terms of b. So that is the variable of integration. That tells you what you're supposed to do to integrate, and then the outcome will be an expression, in the first one an expression of x, in the second one an expression of z, in the third one an expression of b. Now, whatever we get as an outcome through the process of an integration is called the antiderivative. So if I'm going to integrate, this is the integral sign. There are two ways of integrating. There's one way of integrating without using the boundaries. That is called indefinite integration. And then the outcome, which is the antiderivative, is going to be an expression of x. In this particular case, we must add a constant c of integration to the outcome. So once again, if there are no boundaries next to the integral notation, then the integration is known as an indefinite integration. Based on the variable of integration, the outcome or the antiderivative, it's an expression. So if the variable of integration is dx, the outcome is going to be an expression of x. Your final answer must have a simplest form of antiderivative, an expression of x, plus an uppercase letter c representing the constant of integration. The second group is the group known as the definite integration. This is the one that uses boundaries. And this is the one that uses what is known as fundamental theorem of calculus. If that's the case, the outcome is not an expression. The outcome is a number. So therefore, you're not going to add a constant of integration C. We do integrate by using basic rules of integration. And this is true not only for differentiation, but for integration. So we have a table of basic rules of integration. Let's start with some of them. If I'm integrating dx, the d and the integral sign cancel each other out. So the outcome is just x, but this is no boundaries, indefinite integration. So you must add c, which is the constant of integration for all indefinite cases. Another important rule, integrating, and then tomorrow I'm going to give you a table of basic rules of integration, and then a copy of the basic rules, a blank copy of basic rules will be ended out, and we are going to populate that copy together. We start off with some of them on Friday. We are populating fully on Monday. Another important basic rule of integration is known as the coefficient. So what the coefficient rule is saying, if you have a coefficient, I'm going to call it a k, in front of f of x, dx, then we do not differentiate coefficients. We do not integrate coefficients. So the outcome is going to be still k. And then all you have to differentiate is this function f of x dx. Now, as I said, if you differentiate, we call the outcome the antiderivative. The notation of antiderivative is given by, so let me write the notation of antiderivative. So if I'm integrating a function f of x dx, and this is a definite case, indefinite case, no boundaries. Antiderivative, we write it as uppercase f of x plus the constant c. So if I have a rule known as the coefficient rule of integration, we do not differentiate the coefficient. We take the coefficient out, so we are only differentiating f of x. So this is going to be k multiplied by f of x plus c. Another important rule is the constant rule of the first order derivative. Which is very interesting. To get the constant, you have to integrate 0 dx. So f of x must be equals to 0. If you integrate 0 dx, then in that case, you get a constant c only. So that means function f of x must be equals to 0 in order to get only the constant c. Another important rule of basic rule of integration, which we are going to use it a lot, is the power rule. We've seen the power rule for differentiation. Now, the reason why I'm adding this rule, because that's going to allow you to understand deeply the concept of integration being the inverse of differentiation and vice versa. Now, the question is why? Let's look at this. So if we are integrating using the power rule, we still get x, which is the base of the power, but the exponent becomes r plus 1, and you divide by the same number. And then, of course, plus the constant of integration c, which has to be an uppercase c. Now, if you compare this to the basic rule of differentiation, if we differentiate x to the power r, we do not divide by the exponent. We multiply because we bring r in front of it. And we do not add 1 to the exponent. We decrease r by 1, so we minus 1. So that clearly gives you an indication of the concept of learning integration as an inverse operation of differentiation. And then I included some examples in this file. So I highlighted this, that C represents the constant of integration. So this is a typical example where you have a coefficient 5. So you do not integrate coefficients, you take them out. So if I take it out, I'm only integrating dx, and then the d and the integral sign cancel each other out. So what remains is just the variable x. So you have 5x plus c. Now the question is, how come I'm not multiplying 5 by c? You're not, because even if you multiply, everything in that particular constant will be considered as included into the constant c. So there's no need, even the coefficient, there's no need for you to write 5c, because 5c, we still think of it as a c. So that's the reason why we use an uppercase c. That means that we are including any possible numbers that either multiplies or divides c, or do any other operation with c. Here's another example of coefficient 2. You take it out, you differentiate, integrate dx. The integral of dx is x, so we get 2x plus c. Now, what is this particular application? This comes from the sum and the difference rule of the first order of the integration. Sum and difference. So what the rule is saying, anytime you have the sum or the difference of two functions and you're integrating them, so you have an f of x plus the g of x, and you're integrating them, that can be separated into the sum of f of x dx plus the integral of g of x dx. Notice that anytime I write the integration, I make sure that I include the variable of integration. And this is true for the difference as well. So I can kind of like copy and paste this and then simply change the sign to include the option of the difference. So I'm going to put parentheses around this. So you are integrating the difference, and then you separate this into the integral of f of x dx plus the integral of g of x dx. And these particular rules on the sum and the difference are applied in this example when you are integrating x plus 2. So see the separation, you're integrating x, and then you're integrating 2. In each of those cases, notice the presence of the variable of integration dx. Now, the variable x is integrated by using the power rule. You notice that I'm integrating x as x to the power 1 dx. And then if I integrate it, that means according to the power rule, I add 1 to the exponent, divide by the same number. So that means x squared over 2. So I get x squared over 2 plus 2x, because the integral of dx is x plus c. And you have the same very similar example with x minus 2 dx. So these are some examples of integration. There will be more. So you see rules of integration applied. Power rule, integrating x to the power r, and then the comparison with the differentiation to show that connection between the two is inverse operation. And then what I did is I integrated x to the power 3, just as an example. So you add 1 to the exponent, you divide by 3 plus 1, so that's x to the power 4 of 4. But if I have to differentiate x to the power 3, I bring 3 in front of it, that's multiplication, so I'm not dividing. And then I raise this to the power 3 minus 1, so that is decreasing this by 1, or subtracting 1 from 3. So if I differentiate, I get 3x squared. If I integrate, I get x to the power 4 over 4. The other thing that you can notice is the fact that when you differentiate, you reduce the power. When you integrate, you increase the power. And this is where I'm going to stop.